Right, so we've broken this lesson 6 of Unit 2 into a couple different lessons here. So we're going to continue to talk about equivalent equations in the section today and what makes two expressions or equations equivalent and how can we transform one to another and make them equivalent. So we have another situational problem here where it says in family A, the youngest child is 7 years younger than the oldest, who is 18. Write an equation to represent the relationship between the ages of the two children in family A. Explain what each part of your equation represents. So we are given a few pieces here, right? We're given that the youngest child is 7 years younger than the oldest child, who is 18. So we're not given the age of the youngest directly, but we can essentially come up with an equation to represent that, right? And there's maybe a couple different ways you can represent it. So maybe one way you think about it is, okay, well, the oldest child is 18. And I know the youngest child is 7 years younger. So if I subtract 7 off of the oldest child, so this represents 7 years, then that equals, let's just call the youngest child y. So youngest. And maybe you put an 11 here because 18 minus 7 is 11, but I'm just going to represent that idea with oldest child minus 7 is equal to the youngest. Since we're not told 11 directly, we can figure that out. Okay, so hopefully that makes sense. Write a different but equivalent equation for family A. So what's another way of thinking about that same relationship? Think about that to yourself for a second. Well, what if we started off with the youngest? So the youngest child, all right, I'm just going to put child there. So what if we started off with y, which represents the youngest child? And maybe what we do is we say, okay, well, I know the youngest child plus 7, in other words, 7 years, is going to be equal to 18, which I know was the oldest child. So we can see these two equations here and here are both representing the same information, but just in a slightly different way. They're equivalent to each other because they have the same solution. And so if we're thinking about what is the solution that would work here, well, we kind of talked about it on the previous one, but if I put 11 in for y, 11 plus 7 is 18. And I know from the previous one that if I work out 18 minus 7, I get 11. So 11 is the number that fits in for y there. In both equations, you would have a true statement. Okay. So let's think about family B. In family B, the middle child is 5 years older than the youngest child. All right, write an equation to represent the relationship between the ages of the two children in family B. Use m for the age of the middle child and y for the age of the youngest child. Explain what each part of the equation represents. Okay, so let's go back up to the problem here. So I've got the middle child is 5 years older than the youngest child. All right, so middle child is m, youngest child is y. All right, so maybe one way I think about this is, all right, so the youngest child plus 5 equals the middle child. So youngest child plus 5 years, say 5 years, is equal to the middle child. So maybe I think about that. I'm using m for the middle child and y for the age of the youngest. Maybe I could say child age and youngest child age and middle child age. Write a second equivalent equation. Well, how could we think about this a little bit differently but represent the same information? Why don't you think about that to yourself for a second? Well, I think another way that we could represent this information is maybe to think, okay, well, I know there's a 5-year difference So this is kind of like the difference between the ages of them. So if I think of difference, I think of more of like a subtraction problem. So maybe I say this, maybe I say the middle child minus the age of the youngest child is going to be equal to 5 years. So the middle child age minus the youngest child age is going to be equal to 5 years. That's the difference between the two. It's the 5-year difference between the ages. All right, and so I've got a couple equations, a couple of equivalent equations that could represent the same information there. All right, so number 3 then says, Tyler thinks that the relationship between the ages of the children in family B can be described with 2m minus 2y equals 10, where m is the age of the middle child and y is the age of the youngest. Explain why Tyler is right. Okay, so he's going to say that this right here could also represent that situation. And we're essentially saying that he is right. Now we just have to explain why he's right. Well, there may be a couple of different ways of thinking about this, right? We talked about in our previous section how, you can do an operation to an equation, and as long as you're doing the same thing to both sides of the equation, you will create something that's equivalent. Notice really what we've done here is we can relate it to this one. It looks kind of similar. This 2m minus 2y equals 10 looks similar to the m minus y equals 5. And really what we've done is we've just multiplied both of the sides of this equation by 2. And if we do the same thing to both sides, then that's like a legal algebraic move right there. That can transform it into an equivalent equation. So if I do that, I basically use the distributive property on the first one, and I get 2m. 2 times m is 2m, 2 times y is 2y, and 2 times 5 is 10. So Tyler's equation takes the m minus y equals 5 equation and multiplies both sides by 2. All right, so in other words, 2 times m minus y equals 5. We multiplied both sides by 2. In fact, I guess on this other side, I'll just multiply by 2 just separately. So 5 times 2. And then that will give us 2m minus 2y equals 10. And if I divide everything by 2, I get back to the original one. All right, so an equivalent equation can be done if you do the same thing to both sides of the equation, then you can get an equivalent equation. How can we check that though? What if we're like, okay, let's just regular if you say so. But we could check that by putting in some numbers that we know work in the first equation and see if it works in the second equation. So what if I took, think of 2 ages that are 5 years different. All right, so maybe the middle child is 10, and maybe the youngest child is, well, actually, let's make something like maybe the middle child is 18, and the youngest child is, say, 13. 18 minus 13 would be 5. Okay, I guess these are older children at that point. But 18 minus 13 would be equal to 5. So let's see if that works, because that definitely works in the first equation. 18 minus 13 does equal 5. So m minus y does equal 5 in that case. But let's see if it works in the second equation. So is 2 times the middle child of 18 minus 2 times the youngest child of 13, does that equal 10? So I'm just putting it in. I'm putting m and y in here that I chose, that 18 and 13, to see if that works out. So let's see, that would be 36 minus 26, and yes, that does work out to be 10. So same solution, so equivalent. Remember, equivalent equations have the same solution. So I just showed two different ways then. I said back in my purple writing that I can multiply both sides by 2 and I get the new equation. And in my green, I took a solution that I know worked in the first equation and I tried it in the second equation and it also worked. So therefore, the two equations are equivalent. All right, that's where we're going to end my section of the notes today. But if you want to do a little bit more and kind of work through this puzzle down here and see if you can figure out which expressions could be equal to P plus Q, that might be good as an extension problem for you guys to try.